Hi everybody and welcome back. So for today's video we're going to be talking about how we can take our area approximations from last video and actually work towards finding the exact value for the area under a curve. So to do that we have to use some notation and some methods that we haven't really talked about before, one of them being sigma notation. Now sigma notation is something that you would have seen in pre-calculus already. It's a way of representing the summation of a bunch of terms in a sequence that follow some kind of pattern. So we're going to review a little bit about how the sigma notation works, because we're going to need to use this in the process for calculating the actual area. So in general, when we see the sigma notation here, first off, capital sigma is a Greek letter. Whenever we see this guy, it looks like a fancy looking E. That represents a summation of something. So this guy has three main parts to it. So every sigma notation has three pieces to it. So down here, we have what's referred to as the index, which basically means this is the first value that will be substituted into whatever pattern we are using to create the terms that we're adding. So typically, these will start at I equals 1. The variable that we use here, it doesn't really matter what variable we use. It's just whatever variable is used in the index will need to be used inside the pattern itself. But we can really start at whatever number we want to. This just states what value gets plugged into first. And then after that, we move in increasing order by whole numbers. So if I start at 1, I plug 1 in, next I plug 2, and then 3, and so on. If I start at 5, then the next one would be 6. So we only use non-negative numbers, so sometimes we will start at 0, but we don't start with negative values for these. So we start at 0 or 1, and then we keep going on from there. The top guy, this is the upper bound for our input variable. So whatever number we put here, sometimes it could be 5, it could be 1,000 or 1,000. Sometimes we may actually leave that as an unknown variable that we want to control by other means. So sometimes you'll see n written up top there. So that just kind of indicates that the pattern keeps going on and on and on until we get to some unknown value. And then the third spot, I'm going to go back to just leaving this guy as 5 for right now. But then the third spot is what creates the pattern. So this is kind of like the argument. You can think of it in terms of natural log or a radical or a trig function. All that sigma notation means nothing if I don't have some kind of expression attached to it. So that expression is what drives the creation of the different terms that will be added. So we could put any mathematical pattern that we want to here, any mathematical expression that we want, and inside of it somewhere we need to have, if we have a variable, we need to have this index variable, because that's where we're going to pass that number in there. Now the exception to that would be sometimes you may see sigma expressions where all we have is a whole number. So in that case, that means that there is no input, which means when I equals 1, the pattern would produce a value of 6, plus, then I move to I equals 2. When I equals 2, because there's no variable here, means I'm still going to have a value of 6. When I equals 3, same thing. So if that were the case, that just means that it's a constant pattern, so we never actually change the output or the piece that's being added. So we basically just add 6 5 times, okay? So those are all the different parts of this. So what we're going to need to be able to do is recognize some patterns that go on for different kinds of expressions that we use inside of these sigma notations. So first, we're just going to kind of get used to the process and how we go about this. So for the first one, I have the sum from I equals 1 to 5 of the expression I plus 1. So again, when we expand this sigma notation, that means that we want to write out all the terms. So if I'm starting at I equals 1 to 5, then that means there should be 5 terms listed, and then we're going to add them as we go. So when I equals 1, we pass that into the expression. It produces an output value of 2. Plus, then I move on to the next I value. So 2 plus 1 is 3, 3 plus 1 is 4, and so on. So the pattern continues. So then it's a matter of adding all of those up. So if I just go through like normal and add all those up, I get 20. So 2 plus 3 plus 4 plus 5 plus 6 gives me 20. So that would be the value of this summation. Next one, I equals 3 to 7 of the pattern. Oh, I'm sorry, this is actually supposed to be j. Wanted to use a different variable there. If it was I and the variable inside is j, then every value would actually just be j squared because we wouldn't be passing a number into that. But we're actually going to use j equals 3 here instead of I. So when j equals 3, the first value created would be 9. Then when j equals 4, we would have 16, 25, 36, and then 49. So if we go through and add those up, we get 25, 50, 86, 126, 135. So that is our total. So then for the next one, now this one has a few oddities in it that are different from the first couple. So we're using a different index, k. So again, the importance of this is when we look inside of our expression, we have to identify that input variable because that's the only part that can change its value. Everything else in that expression will stay the exact same for every term that I create. So for example, when k equals 1, this 1 over n, even though it's a variable, it's not the same variable as my index. So that means that that expression would just be 1 over n times 1 squared plus 1. So that would be the first iteration of this. When k equals 1, that is the term that's produced. Now, obviously, we can do some simplifying there, and we'll do that in a second. But just from the substitution, that's what I end up with. Now, when k equals 2, second iteration, 1 over n is still out in front, but now we have 2 squared plus 1 inside. And then when k is 3, we'd have 1 over n times 3 squared plus 1, and so on. Now, the upper bound of the summation, this time I don't have a number chosen. So that actually means that we would just keep writing out the next term on and on and on until we get to what we refer to as the nth term, or the last one. So this n just kind of takes is a placeholder. So if we would pick a value of n, then we could substitute it in this spot and anywhere else that it shows, which just creates an extra piece to this pattern. So when k gets to n, then at the very end, we would still have the 1 over n in front, but then we would have n squared plus 1 for that last piece. Now, for this one, because this is a an infinite kind of pattern, because we haven't chosen an end value for n, we couldn't actually total this guy yet. We wouldn't know what it equals. However, if you do notice, there is a little commonality here between all these terms. Every single piece of this sum would actually have a 1 over n term in it. So because of that, because the sigma notation is actually just a representation of repeated addition, what we notice is that anything that shows up in every single term, to speed the process up, we could actually factor it out. So we would actually have 1 over n that we can take out from everything, and then this term would be 1 squared plus 1 is 2, plus 2 squared plus 1 is 5, and then 3 squared plus 1 is 10, and so on, all the way up until this very last term, which would be just n squared plus 1. So again, we can't actually get to a final answer for this guy right now because n isn't chosen for us. But if we picked a value of n, then we could actually use this formula or this expression to figure out what that total is. So just a unique thing with the sigma expression. So if you notice that we have anything inside of this argument spot that does not match with the variable for the index, then what we can actually do at the very beginning is pull that whole thing out in front. So we could actually rewrite this as 1 over n times sigma from k equals 1 to n of whatever's left over, k squared plus 1. So just a special property for our sigma notations. Another way of exploring it, and this notation will be relevant to us here shortly, if I had something like the sum from I equals 1 to n of f of x sub I times delta x, Well, again, if I just wrote these terms out verbatim, exactly what the notation says, then when I pass 1 in, I would get f of x sub 1 times delta x, plus, then when I equals 2, we'd get f of x sub 2 times delta x, and so on and on and on until we get to f of x sub n times delta x. Or once again, you notice we have a delta x factor inside of each one of those terms, so I could really pull that delta x out in front, and it leaves me with f of x sub 1 plus f of x sub 2, dot, 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 all the way up until the last of those f of x values. And if you really think about it, this should look fairly familiar because this is really the setup of our area approximations from our previous section. So really what's going on here is we're just finding that total of all those heights and then multiplying by the common width. So it's just another way of representing that same pattern or same structure that we saw last time around. Now we're going to take a look at ways to speed up this summation process. So years ago, centuries ago, mathematicians who were exploring and experimenting with these summations and just different patterns in general realized that when the structure of the expression that is creating the terms being added in the series follow particular formats, then there were fast ways to get to that summation. For example, if the argument or the expression inside of our summation is simply just a constant, then when I expand it, all we have is a bunch of those constants being added together n number of times. So n number of c's added together really is just equal to that constant times however many terms we have, or n. So this is a shortcut way of getting to the answer whenever that argument is simply just a constant term. Then, so again, this would be a constant pattern. If we had something like I, or that's really I to the first, this is kind of like the linear pattern, then in that case, all we have to do is follow this special formula, n times n plus 1 over 2. So this formula comes from a mathematician who realized that when looking at an arithmetic sequence of terms, there's a way to fold that series on top of itself. So for example, if I had 1 plus 2 plus 3 plus 4 plus 5 plus 6, so that would be 6 terms all generated by the pattern from I equals 1 to 6 of just I. So again, that perfectly matches this notation, but now I've chosen a value for n. Now when I fold that series on top of itself, and what I mean by that is I'm taking the first and the last and pairing it, the second and second to last and pairing, third and third to last to pairing. All of those pairs end up equaling the exact same total, or n plus 1. 6 plus 1 is 7, and that's exactly what each of those pairs adds up to. Now the rest of that formula, n over 2, 6 divided by 2 is equal to 3. That's actually the number of pairs that I end up with in that series when I fold it on top of itself. So the shortcut way of getting to this is take your n, add it to 1, or add 1 to it, so that gives me 7, and then n divided by 2 is the number of pairs that total to that value. So I know that the first 6 integers added up is 7 times 3, or 21. Actually, I guess I should write that down here. So that's the arithmetic formula. So this is a shortcut way of evaluating any sigma notation of the form I to the first. So that's the linear pattern. Quadratics operate in a similar fashion, just a slightly more complicated formula. So when I take the summation of I squared from I equals 1 to n, its formula is n times n plus 1 times 2n plus 1 all over 6. So it's a little bit more advanced, more complicated formula, but you'll get the hang of it once we try it out here in a few minutes. And then the last one, this is for a cubic. I cubed generates the formula n squared times n plus 1 quantity squared all over 4. Now, there are other patterns for other degrees of polynomials, or the I patterns here, but this is really all we need for the work that we're going to be investigating and taking a look at. And again, this is not our main focus for this unit, but these summation formulas are going to help us speed up our process of where we're actually heading. So we're going to have to get used to these before we can actually apply them. So let's try one. So the key here is getting the arguments down to just one of these pieces. So if you think about some of the stuff that we have seen already, let's say, for example, I had an expression 3i plus 2, and I go from I equals 1 to n. Well, the very first term of that would be 3 times 1 plus 2. Okay, that would be from the first one, plus from the second one, it would be 3 times 2 plus 2. Then from the third, 3 times 3 plus 2, and on and on and on. If you see, every single one of those terms that are created has a plus 2 in there. So not only can we pull out common factors from all of those, but what actually ends up happening is when you have more than one term inside of this argument, we can actually separate this and create two separate series. So a series is the technical name for the sigma notation, because we're taking a sequence of terms that are created and we are adding them together. So all I have to do is separate it at the plus or minus sign. 3i would generate the pattern of 3 times 1 plus 3 times 2 plus 3 times 3, and the sequence or the series of 2 would just create 2 plus 2 plus 2, and so on. So our goal in doing this is to try and strip away all of these parts so that we are left with just a constant I squared or I cubed inside of our argument. Once we have that, then we can replace them with these formulas. So, for example, let's try this one. It says I equals 1 to n of the expression I plus 1 over n squared. So again, my goal is to strip away some of this stuff. So the first thing I need to get out from the inside is the dividing by n squared part, because that is not controlled by my index. So that would be a factor in every single term that I generate if I expand this out. So the first thing I'm going to do is rewrite this as 1 over n squared. Again, I can pull those extra multipliers, so an extra constant or factor that we're multiplying by, out in front. So times the sum from I equals 1 to n of I plus 1. And now from there, because this inside has more than one piece to it, I am going to split this into two separate sigmas. But each one would have the 1 over n squared in front, because I pulled that out in front before separating it. So the first one would become 1 over n squared from I equals 1 to n of just I, plus 1 over n squared times sigma from I equals 1 to n of the second term, just a constant, or 1. So now, because each one of these sigmas has been broken down into just one piece, either a constant, I squared, or I cubed, we can now go back to these formulas and replace them. So now this sigma of I will be replaced with its formula. So I'm going to rewrite this result as 1 over n squared times n plus 1 all over 2. And then plus from there, now we're going to go to the second piece. This constant sigma can be replaced with the constant formula. So in this case, my c value was just 1. So it literally would just be 1 plus 1 plus 1 plus 1 over and over again n times. So by the end of it, I have n number of 1s added together. So I have a total of just n. But I still have that 1 over n squared out in front. So what this does, this process of using these little formulas, it generates an expression that only depends on the value of n. So what that means is if you go back to the beginning and I tell you exactly how many terms that you need to actually expand out and create, then this is a formula that will quickly calculate the total of all those terms for me. So for example, and we're going to do this one a little bit in an expedited way, but if I go back to the very original notation, instead of using n, I'm going to substitute in 10 at the start of this. So from I equals 1 to 10, I want to find the value of I plus 1 over n squared, which again, I'm plugging 10 in. so over 100. And now I'm going to actually list out all of these terms. So when I do that, I would get 1 plus 1 is 2, so 2 over 100. And then when 2 goes in, I would have 3 over 100, 4 over 100. So I would have the first 10 terms in that sequence all added up together. So all the way up until 11 over 100. Whoops, plus, not equals. Got ahead of myself. So what I would like to be able to do now is quickly add all of those up. Now, if I've already expanded them, then I can just sit here and add all those numbers up, but that's kind of annoying because A, it requires me to expand this thing the whole way out, and then it makes me have to actually do all of that math and add it up. Now, for the sake of doing it here, I'm actually going to use a little shortcut here. I know that each one of these pairs is going to add up to 13. 2 and 11, 3 and 10, 4 and 9, and so on. There are 10 numbers there. Cut them in half. That gives me 5 pairs of 13. So it adds up to 65 out of 100. Okay? That's the actual answer here. Now we're going to show how this formula will generate that without needing me to actually expand this whole thing out. Now to do that, I need to go back through here and do some simplifications. For example, 1 over n squared is a part of both of these, but I can actually reduce here. There's a factor of n on top, which will cancel out with one of those. Same thing here. This factor of n cancels out with that guy. So what I end up with here is actually n plus 1 over 2n plus 1 over n. To be able to combine those, I would just have to multiply top and bottom by 2. So in this case, I would get n plus 1 plus 2 over 2n, or n plus 3 over 2n. So that is the final expression. That is the value of this sum. So again, at the beginning of this, I chose 10 as my n value. Well, if n equals 10 and I substitute that into this formula, I get 10 plus 3 over 2 times 10, or 13 over 20. If I were to reduce 65 over 100, both are divisible by 5, that produces 13 over 20. The exact same thing. So that is the idea. These little I formulas are ways of recognizing a pattern and giving us kind of a shortcut to get to the final value, no matter how many terms or pieces of that puzzle I decide to expand to and add up all together. And that's going to be huge for what we're going to do here in a few minutes as far as our area stuff goes. So now that I have this formula right here, again, that gives me the sum for the first n terms in this series. Now, again, if I wanted to up the n value to something bigger, to 100, I don't need to sit here and expand and write out the first 100 numbers altogether, because this is my shortcut formula. So when n equals 100, I would get 100 plus 3, or 103, over 2 times 100, or 103 over 200. If n was 1,000, then again, I just plug that number in. So the first 1,000 terms in this series would total up to 1,003 over 2,000. If n was 10,000, it's going to get even bigger, or all the numbers get even bigger. 10,003 over 20,000. So what we're able to do with this, again, everything in math is about exploring patterns and being able to recognize trends and tendencies. If we look at this, as these numbers, or as our n value gets bigger and bigger and bigger, which means I tack on more and more pieces to this series, hopefully you guys see some trend, something that's happening here. If we were to look at decimals for these, this would be 0.65, or excuse me, not 0.65. Yeah, sorry, 0.65. Let's do, I don't know, 103. Actually, yes, I do. That would be 0.515. This would be 0.5015. This would be 50015. So hopefully you guys see what's happening here. These numbers are actually going to begin approaching something. And that's what we need to kind of kickstart in our brains and start thinking about as it relates to our area stuff. This n pattern, for as n gets bigger and bigger, the total, or this sum formula, is actually approaching something. So we need to kind of be able to think about that in our mind moving forward. All right, so now we're going to take what we just talked about with our summation stuff and try to link it into the area approximation stuff from last section. So by now, we know how to estimate the area under a curve with that repeatable process. So we find delta x, we use that to build a list of endpoints, we pick which endpoints we want to use, then we calculate the heights at those endpoints, we take our common width, delta x, multiply it by the total of the heights, boom, there's your area approximation. So that was our repeatable process. And now we know how to use the summation properties. So what we're going to try to do is combine the two to make finding that area for any number of rectangles, including really, really big numbers. So all the examples that we looked at in section 2 with the area approximation stuff, you had a very small finite number of rectangles, usually about 5 or 6 at most. But as we start to increase that, that's where we start to see some really interesting patterns. So for example, suppose we wanted to use 100 rectangles to approximate the area of a region. If that were the case, our endpoints would all involve really difficult values to substitute into the function. So even if it was like a nice interval, like say 0 to 10, then each one of those would be a small decimal value that we have to plug into a function. So whether it's a squared function or cubic, all of those are going to be really tedious and difficult values to substitute in. So it's going to take a long time. So instead, we're going to try to utilize our sigma notation properties to help us jump right to the very end. We can actually skip over all of that tedious process of substituting in each different endpoint value to get each individual height. Because we kind of know where we're headed in the long run here with the sigma notation, we can use that to generate an expression that depends on the value of n, and then we can use that to find the approximations for any value. So this is the general process. This is how this is going to work. So our area will be approximately equal to sigma from our first subinterval to our last. And for each one of those, I want to take the height of the rectangle multiplied by its width. That's not really anything new except for using the sigma notation. So again, worst case scenario last time, if we had unequal subintervals, we would have done the same thing. Our area would have been approximately equal to the first rectangle's height times its width, plus the second rectangle's height times its width, and so on, all the way up until the very last one. So that's not really anything new. The only new part there is shrinking all of that down and representing it with that sigma notation. But it still operates the same way. But now what we can do is take this very generalized concept or way of writing it and make it more specific to what we're going to be working with. So now instead of saying height, remember the heights of the rectangles really depended on the y value of the function, and the width we actually calculated and represented it with that delta x quantity. Okay, well, to calculate those y values, remember we took an endpoint and substituted it into whatever the equation of the function was. So we represented that by f of x sub I. So that notation, now again, this guy right here, that was actually one of the examples from earlier in the video. That's why I said this was going to come back. So from now on, whenever you guys see our f of x sub I notation, you need to associate that with a height. That represents a y value on a curve, which we can use to dictate the height of a rectangle that we choose to use. So notationally, I want to go from the first subinterval to the last, and for each one, I'm going to take the value of the function f at some x sub I value, so some endpoint, and then multiply it by that common delta x value. Or remember, the formula for delta x is really that b minus a over n value. Instead of saying first and last, we can use the proper notation with our sigma, where we say I equals 1, so that represents the index, that's the first subinterval, and then n is just however many rectangles I choose to use. So what we get here in the end is a formal and appropriate way of representing the area approximation for equal subintervals for any number of rectangles that we choose to use. So again, that x sub I, though, it represents either the right or the left endpoint, and then that value of I is dictating or controlling which individual subinterval we are currently working in. But again, it just works like all these other sigmas. You start at 1, plug it in, do all your math, get your stuff, then go back, plug 2 in, 3 in, 4 in, and so on till we get to n. Now, what we have to go through is a little bit of a process on mathematically representing all of those different endpoints. So if you remember, the way that we generated that list of endpoints, it was all dictated by A and then your delta x values. So remember, the entire list of x sub I, we would always start at A, and then it was A plus delta x, and then A plus 2 times delta x, A plus 3 times delta x, ... all the way up until the very last one, where it was A plus n delta x. So by the end of that, we have the whole list. But remember, if I want to use left endpoints, then we are actually going to start with our A values. So that was going to be, remember, it's everything on that list except for the very last one, A plus n delta x. So to represent all of those guys, we have to come up with some kind of formula that depends on the value of I. That way I can use it inside of this sigma notation. So that's where this formula comes from. When I am trying to generate left endpoints, I am going to use the formula x sub I equals my A value plus delta x times I minus 1. So if you really think about that formula, what it says is that when I equals 1, if I stick 1 in here, well, 1 minus 1 is 0, delta x times 0 is 0, and A plus 0 really equals A. Then when I equals 2, I would get A plus delta x times 1, or that second guy. So this formula is just a way of creating this list of values. But we have to have this in order to work with this new notation inside of sigma. Now, for the right endpoints, we have to shift everything to the right one in that list. So for right endpoints, if you notice, the only difference is we lose the minus 1. Instead of shifting everything back a step, we just leave it where it is. So now if I try to test this out, when I equals 1 for the right endpoints, again, the first subinterval would go from A to A plus delta x. So if this works out correctly, my first right endpoint would be this guy. So when I equals 1, if I substitute that in here, there is no subtracting here. Now it's just 1 times delta x, which is delta x. So we do, in fact, end up with what we wanted. Then when I is 2, we would end up with A plus 2 delta x, which would be that correct second right endpoint. So these formulas are important for us because we're going to have to use those in the function's equation. So again, to use either of those formulas to actually generate endpoints, we'd just be actually plugging in the values for A and delta x. Then we just keep plugging in new values for I. So, but when we are doing this in a theoretical sense, we need to have these formulas so that we can actually plug in these expressions into the actual function. So when you use that sigma notation, if we just put A and delta x into the formulas, that leaves the I as an unknown. And what that's going to do is that's going to create an expression that we can then plug into the function f of x, then use our sigma notation to generate those expressions of n. Remember, that's our end goal. We want to turn all of these I things into the n's from earlier so that we can use those to quickly calculate the value. Now, there will be some times where you're told strictly use left endpoints or use right endpoints. But if you are ever given a choice out of these two formulas, I would always want to use the right endpoint. That formula is way easier. We don't have to subtract anything, so that's just going to keep our math much simpler. So, enough talking about it. Let's actually dive in and try one. So this is going to be a full-blown problem from start to finish. So we are going to suppose the function f of x equals x squared is graphed on the interval 0 to 2, and we're going to use sigma notation to generate a formula for left and right endpoint approximations, and then we're going to find the value of those approximations for 3 different values of n, okay? So the reason why we had to have those x sub I formulas is because a problem like this. If we don't say ahead of time a definitive value of n, then we have to start from scratch every single time. I have to take delta x for when n equals 5, use that to find all those different values of x, then do my whole long area approximation process. And then when n equals 10, you generate new numbers. So when you make it specific, you actually make it more difficult. A lot of people think, well, working with numbers is easier than working with variables. But when you set specific parameters, then your calculations have to start from scratch every time. So what we're going to do is we're going to leave this very generic and unspecific from the get-go, okay? So for that, we'll do left endpoints here on the left, and then we'll do all the right endpoint stuff on the right side here. So for our first step, for both, we're going to find delta x first. So remember, delta x is b minus a over n, but we're going to leave n as an unspecific value to start, okay? So in this case, b minus a would give me 2 over n. 2 minus 0 is 2, and we're going to leave n as an unknown value for the time being. So because of that, now I am going to take that expression, and I am going to generate my list of endpoints, or a formula that would calculate all of the different endpoint values for me. So again, for left endpoints, we are going to go back and use this guy. So I'm going to start at my a value, which in this case is 0, which is nice. Definitely easier when a is 0, plus my delta x value, 2 over n, times I minus 1. Or in simple terms, 2 over n times I minus 1. I don't have to leave that 0 plus in there. So this value, this expression generates all left endpoints in the interval. And again, if I chose a specific value of 5 right now, and then I went through the cycle of I equals 1, I equals 2, all the way up through 5, this formula would calculate those for me immediately. Again, I don't want to do all of that right now because I want to keep this very generic, but if I needed to actually come up with the numbers, I could do that with that formula. So just like the previous process, if I actually had a list of x values, then the next step would be plugging all of those into the original function to get all of the heights. But again, we're doing this in a generic mindset. So because this is just a formula for the x values, we still need to pass this formula into the function. So that's our next job. We need to find a formula or an expression to calculate the heights of all of these endpoints, or in other terms, f of x sub I. So if f of x is x squared, then f of x sub I would be instead of x squared, we would take all of this stuff and square it. So we end up with 2 over n times I minus 1 quantity squared. It does not look nice. So what that really means is we need to square all of this stuff. So the fraction in front, we can just square top and bottom. That part's not too bad. So we end up with 4 over n squared. Then for our binomial squared, for that guy, we would just expand. So we get I squared minus 2i plus 1. So next, if you really think about what it is that we're doing, again, the general structure of these is based around the idea that area is approximately equal to the sum from the first to the last rectangle, and for each rectangle, we take its height times its width. But for these problems, the way that we have notationally represented each of those, we are going to set up the sum from I equals 1 to n of the heights are now represented by this expression. Or another way of thinking about that, if I were to choose a value of n, so I choose how many subintervals I want to break the interval up into, and then I tell it which subinterval to work with, so I pick a value of I, then that will generate the value of the height for that rectangle. So I'm going to take that and substitute it in here. So 4 over n squared times I squared minus 2i plus 1. So that's all my height. And then we need to multiply that by the width of each rectangle. But again, for our notation, we use delta x to represent the width of each rectangle or subinterval. So that is what I'm going to multiply by down there at the very end. So this whole sigma notation now represents our area approximation. But now what we need to do is clean it up a little bit. So this is where our summation stuff comes back into play from earlier. So our goal now is to turn that one summation into several of them, where the inside of each one is just a constant I squared, or I cubed. Obviously, we don't have any I cubes here, so it's really just going to be those first three. Now, remember earlier we looked at a couple examples where if we have extra factors that the variables in them, or if they're just constants, don't match up with the index, then we're allowed to remove those and bring them out in front. Because if I did expand this guy, every single one of those would have a 4 over n squared and a factor of 2n. So if I combine those or multiply them together, I can actually pull out a factor of 8 over n cubed from the inside. So what I end up with is 8 over n cubed times the sum from I equals 1 to n of I squared minus 2i plus 1. So from here, now we are going to take that one sum and chop it up into its three pieces. Again, we have three terms, so we would separate this guy into 3 sigmas. Now, since 8 over n cubed is out in front, rather than writing it 3 times, I'm going to put some big brackets around this thing. And I'm just going to break it up inside. That way I can just keep the 8 over n cubed, all the way out in front. There's no need to write it multiple times. So this will turn into 8 over n cubed times, and then on the inside, I will have the sum from I equals 1 to n of I squared, that's my first term, minus, because there's a minus there. Now this 2, that coefficient, if I put 2i inside, then I can't use my formula. But that 2, again, is an extra factor that I can pull out in front. So we end up with 2 times the sigma from I equals 1 to n of just I. And then my constant is going to get its own sigma down there at the end, I equals 1 to n of just 1. So again, look at that, make sure the structure of everything makes sense to you, how we got there. Again, I just took my one big polynomial expression, chopped it up into its individual terms, and I take the sum of I squared minus the sum of 2i plus the sum of 1. So it works just like with a regular polynomial. We can do the terms individually. But because we did that, now each one of those looks identical to one of our n formulas from above. So now we're going to go through and replace each one with the corresponding formula. So yes, I know these problems are long, but good news is we're working towards a process that'll be super quick, but this is laying the groundwork for all of that. So I have my 8 over n cubed out in front, and now inside, each one of these is going to get replaced with its own formula. So let's start with the first one, I squared. Well, you can scroll back through or flip it back over. But for that guy, its formula was n times n plus 1 times 2n plus 1 all over 6. Okay? Now, second formula. So it's really just the sigma of I that I'm replacing. So this minus 2 is actually just going to come down and be a factor out in front. So that works for any kind of coefficients. So we can just bring that down in front. But then the formula for I was n times n plus 1 all over 2. Then for our last one, replacing the sum of a constant from I equals 1 to n, that, remember, is just n times whatever that constant is. So in this case, 1 times n is just n. So by the end of that, there are no more i's. And again, that was my goal. Our goal is to create an expression that just has n in it. because now what I can do is now we can go back and use all these different values of n to explore if I did chop it up into 5 pieces or 10 or 100, what would that area give me? It allows me to skip over that really annoying process of sticking every value of x in, generate the heights, then add all of them up and multiply. Yes, this looks like it's way more complicated and takes longer, but that's because we're doing all of the math for every possible value of n. So instead of having to do each one individually, this will take care or make it possible to evaluate for any of them. And then that allows us to explore even more things. So now all we have to do is go through and clean this guy up as much as possible. So to do that, we're going to do some expansion inside, and then we're going to distribute this 8 over n cubed stuff in here. So I'm going to do a little bit of math for us just to help speed the process along. This inside part, if I multiplied all of this stuff in the top together, if we expanded all of that polynomial stuff, I would end up with, let's keep 8 over n cubed out in front for right now. This would end up being 2n cubed plus 3n squared plus n all over 6. And then here, these 2's are actually going to cancel each other out. So we actually just end up with n squared, but it's a negative, so I'm going to distribute the negative. So minus n, and then we still have the plus n at the end. So now I need to go through, clean this up. So these n's actually cancel one another out. So I'm left with this fraction minus n squared. So I'm just going to go ahead and turn this into a common denominator, multiply top and bottom by 6. So now I can combine 3n squared with negative 6n squared. I scroll down just a little bit, we can get to our final answer here. So for this one, we would end up with 8 over n cubed times 2n cubed. 3 minus 6 would give me negative 3n squared plus n all over 6. And if I want to multiply this, I'm going to reduce 8 over 6 first. So this turns into 4 over 3. So we end up with, if I distribute the 4 across, 8n cubed minus 12n squared plus 4n all over 3n cubed. That formula is what I need here. So in this case, for this problem, to use left endpoints for n number of sum intervals to calculate or estimate the area under x squared from 0 to 2, if I used n equals 5, then my area approximation would be approximately equal to whatever this expression equals when I substitute 5 into it. So let's do some, actually I'll just use Desmos here. So we have, and actually let's speed up the process. Let's say that f of x equals 8x cubed minus 4x squared plus 4, and again, I'm using x's, but that's just because Desmos doesn't like n, plus 4x, and then over 3n, whoops, 3x cubed. Let's just double check. 8x cubed minus 12x, oh, excuse me, 12x squared. All right, so now if I want to substitute 5 in, I get 1.92. So that is the value of this when n equals 5. So if I were to go through and do all of the substitutions here, do all the math, that's what my area equals. Okay, now when n equals, what was our next value? N equals 10. So if I try do the same thing, f of 10, now I get 2.28. And then let's do one more when n is 100. F of 100 gives me 2.6268. So we'll say 2.2627. All right, so that's it. So some of you might be wondering, well, why do we need to do it for different values of n? Well, if you really think about the idea of this process, I'm taking a finite region, like the graph of x squared from 0 to 2, and I am trying to fit inside of that at first 5 rectangles. Well, that's not too bad. First one with the left endpoint would be flat, and then 2, 3, 4, 5. Okay? Now remember, 0 to 2, that function is increasing, so my left endpoint is always going to be sitting below. So these are actually always, underestimates for this actual area. But if that's the region and I try to fit 5 rectangles in there, you guys can see how tight those are. Well, if instead of 5, if I try to squeeze 10 rectangles in there, the rectangles themselves are going to get really skinny. So really skinny, but it's also going to better fit to the region. Because instead of having so much extra space left over inside of that, the extra rectangles get closer to the curve. And so what ends up happening as I increase the number of rectangles that I try to jam in there, the estimations are actually going to become better and better and better. So what's actually going to happen is we're actually going to start to get closer and closer to the real deal. That's the whole idea of improving estimations. The better an approximation is, the closer to the real thing it is. And that's the key here. That's why this formula is so important to us, because having it allows us to stick in all kinds of values of n and evaluate it super easy. For example, let's say that I tried to plug or fit 1,000 rectangles into that region. Then we get even closer, even better estimates. So we can start to increase more and more and more, and you guys can start to see these values seem to be approaching something, which is really important to us. That's the idea of a limit. We've used that in the past for calculus processes when we were estimating the slope of a tangent line by using a secant line and making that estimation better and better and better. That's what's going on here, okay? So that is my left endpoint Riemann sum. Now, let me get rid of all this junk. Now let's try the same thing, but with the right side. And you guys are going to see, I don't want you to think that this right side is going to take 20 minutes just like the first one did. You're going to see the right side is actually way faster and easier, especially because we've gone through a lot of the nuts and bolts stuff. This one will go much, much faster. So, but a good chunk of this is going to be the same idea. So my delta x is still the same, still going to be 2 minus 0 divided by n, or 2 over n. But now we get to use that easier x sub I formula. So again, for right endpoints, we don't have the I minus 1. It's just simply I that's being multiplied. So in this case, it would be 0 plus 2 over n times I, or the simplest way to write that is just simply 2i over n. So if you compare these two, again, this is why I said if you have a choice between left or right, doing the math with this formula is way easier, no matter what the equation is, than this guy. Because now when I go to substitute my x sub I formula into f of x to get my heights, now all I have to square is this fraction. That's way easier than having to square that binomial. It also is going to make our summation stuff much simpler as well. So my formula for f of x sub I is actually just 4i squared over n squared. So that's really easy. 10 times easier than what we just did. So now if I set up my area formula, again, this will be the sum from I equals 1 to n of my heights times my widths. My height formula is 4i squared over n squared times my width formula, or delta x, is 2 over n. And just like before, if you guys notice, I still have a 4 over n squared and a 2 over n factors in there. So really the only thing left inside that's going to stick around this time is going to be this I squared. All these other things can be combined and moved out in front. So that would leave me with the sigma of 8 over n cubed, just like we had before, times the sum from I equals 1 to n of just I squared. Because it's just that one term, that actually means I don't have to do any breaking apart or anything. We can jump straight to replacing that sigma with its formula. So that means we end up with our area being approximately equal to 8 over n cubed times the I squared formula, or n times n plus 1 times 2n plus 1 all over 6. So you guys can see how much faster and simpler this one has been. So now I can expand inside of here again. This is always going to be the exact same result. So what I have right here, it's going to be the exact same thing over here. So I'm going to go ahead and distribute my 8 over n cubed. Or actually, let's reduce this back down, 4 over 3 again. So I'm going to go ahead and just multiply this final result out. So what I end up with is 8n cubed plus 12n squared, and then plus 4n, all over 3n cubed. Okay? So now we have our expression to evaluate the area for the right endpoints. So now we can do the similar process and just go through the different values of n. So if n equaled 5 for the right endpoint, we can plug that into this guy. So let me change our formula here to match the right endpoint now. So this guy would be plus 12 x squared, in this case for Desmos, plus 4x, okay? So now for this side, we want f of 5. So for this one, we have 3.5 for our area, 3.52. Now also keep in mind, we said that the left endpoint was the under because, again, for the function of x squared, we are increasing. So between any two endpoints, if I pick the right endpoint, now we're going to be sticking out above. So we know that all of these estimations are going to be above the real thing or overestimates. So just like we saw these values approaching something, but they're doing it from the lower side, we should see that these are approaching something, but now they're doing it from the top side. So we should be approaching downward towards something. So when we use 5 subintervals, we get an approximation of 3.52. If I up that to 10, then it comes down to 3.08. If I go to 100, 2.7068. Let's see, how far do we go? 100. I think we went a little bit further for the left endpoint. So if I keep going to 1,000, then let's just jump it way up here to 1,000,000. Then you guys can start to see now that number should look familiar. That was actually the same value that we were approaching from the other side. So what does that mean? Well, that's the whole ball game. What we just figured out there was that for the left and the right endpoints, as we keep increasing the number of rectangles that we use to estimate this area, we actually start to approach the same value. That is the idea of exhaustion. If I keep increasing the number of rectangles that I use on both sides, so again, left is my under, right is my over, if both of those approximations get more and more accurate, eventually we're going to squeeze the real value super tight in between these two approximations so well that we can actually get it to approach the real deal, the exact area under this curve. And that's where we're going. So the idea of increasing the number of rectangles infinitely is the same thing as taking a limit. Remember, that was a similar process that we've done in the past. So again, what we had here before was for our left endpoints, the area was approximately equal to, you copy this formula down, 8n cubed minus 12n squared plus 4n over 3n cubed. Thanks. Then for our right endpoint, that formula was that area was approximately equal to 8n cubed plus 12n squared. So that was really the only difference in those two expressions, and that was what forced the left endpoint to be below and the right endpoint to be above, plus 4n over 3n cubed. So now what we want to do is we want to say, well, what happens if we do continue to increase the number of rectangles infinitely? Well, to evaluate that or to explore what that area approximation would approach, that is where we are going to require a limit. So I'm going to take the limit as n, because n is the driving variable in these expressions. As n approaches infinity, that means the number of sections that I use increases infinitely. But if you really think about what that does, as the number of rectangles gets bigger, then the width of each one is actually growing infinitesimally small, or super, super thin. Okay? So the limit as n approaches infinity of this expression. So of 8n cubed minus 12n squared plus 4n over 3n cubed. So if I do that, this just goes back to our old limit stuff. There's several different ways to approach this. The simplest way is, again, it's just a rational function. So look at the growth rate of top and bottom. I've got a cubic over a cubic, same over same, means my limit is equal to the ratio of the leading coefficients, or 8/3. 8/3 as a decimal is 2.66 repeated. That is the decimal that we were approaching when we were looking at those values. Now, let's do the same thing, but for the right side. So if I take the limit as n approaches infinity of this expression, well, we said the only difference in these two expressions was that middle term. The left endpoint was minus 12n squared. The right endpoint is plus 12n squared. But when we took the limit of the left side, or the left endpoints, the middle term doesn't mean anything, because as n gets really big, it's only the leading term that actually does anything for us. So this is still same over same, and therefore that limit is actually going to be the exact same value as the left side. So what that tells us is the area approximations on the using left endpoints and the right endpoints, or the underestimates and the overestimates, as we increase the number of rectangles that we use to approximate the area, those two values will approach the exact same thing, and that exact same value is the actual area under that curve. When we sketch the area under x squared from 0 to 2, that region, that weird shape that is bordered by that quadratic function, has an exact area of 8/3. Now, to you, that might not seem like a big deal, but to any math nerd or anyone that has any sense of geometry, that's pretty wild that a weird, non-traditionally geometric shape like that can have a finite value area, or something that we can possibly use math to calculate. But that is the amazing power of calculus, and the fact that we can apply it and find something like that. So for us, being able to do these problems, we just discovered a major thing. We now know how to find the exact area under any curve on a given interval. To do it, we simply need to take the limit as n approaches infinity of the summation from I equals 1 to n of f of c sub I times delta x. Well, c sub I, that's a noticeable change from the way that we were writing it before. Before it was x sub I. Now I changed it to c sub I. I like to think of c sub I as your choice. So what we just discovered is that if we do this process with left endpoints or right endpoints, it doesn't matter, because when I take the limit of either of them, it approaches the same thing. And that is always going to be the case. So when we write this notation, I want you to think of it as it's our choice of either left endpoints or right endpoints. And again, we said earlier, if you have a choice, we should definitely always be picking our right endpoints. So we still technically need to write c sub I, just so in case for some weird reason you would want to do left endpoints, know that you still have that choice. But we're always going to do right endpoints when we do problems together. So all that means is we're just going to do what we just did before. Again, we don't have to do both. We're only going to do the right endpoints. But then once I get it down to that n expression, we just take the limit of it. That result is going to be our exact area under the curve. So now we can do any of these problems super quick, easy, and we can find the exact area, we no longer have to do any of the estimation. We can find the real deal. So let's try a little bit more difficult one. So for this one, we're going to find the area of the region bounded by the graph f of x equals x cubed, the x-axis, and the vertical lines, x equals 0 and x equals 1. So really all that's a mouthful to say. It's the area under x cubed from 0 to 1. So these x values are my a and b. Okay, it's just a different way of expressing the boundaries for that region. So we're going to start off, same process as before. We're going to find our delta x. So in this case, 0 to 1, that would be 1 divided by n. Again, delta x is b minus a over n. Notice that nowhere in this did I say estimate or did I say a certain number of subintervals. All I said was find the area. It's no longer an approximation because we know how to find the real thing. And we don't have to worry about a certain number of subintervals because we're going to use a placeholder n, and then we're going to force that number to go to infinity. That's what allows us to find the real thing. So we have our delta x. Now instead of x sub I, I'm going to use c sub I. But again, my choice is always going to be right endpoints. So I'm going to take a plus delta x times I. That's all I got to do, as long as my tablet doesn't freak out on me. So a is 0, and then delta x is just 1 over n. So 1 over n times I would just result in I over n. So, now I have a disappearing I. So my formula for c sub I is I over n. So that is the formula that will generate my x values. So now I can use that to find a formula for my heights. So f of c sub I is, again, just the result of taking this expression and sticking it into our f of x for x. So if I take I over n and I cube that, then I just get I cubed over n cubed. So that is my expression that I will use to generate my heights. So again, from there, every rectangle's area is just width times height. So you see this diagram with we call this a representative rectangle. It's kind of just a visual cue to remind us that we are taking each of those rectangles, multiplying width times height, and using it to generate the area. So all I really need to take is this guy times my width and take the sum of it. But again, now some notational changes. I no longer need my squiggles because I'm no longer approximating it. Now we turn it into a firm a equals, and we now also, because it's equals, need our limit notation. So I'm going to take the limit as n approaches infinity of the sigma from I equals 1 to n of my height, so I cubed over n cubed, times my width, 1 over n. Can fix my tablet, that would be great. And again, just like in past, any of those extra non-I factors we're going to combine and move out in front. But we don't move it outside of the limit notation. The limit notation is going to be in front of everything. So I do like to put brackets up just to make sure it's clear what we're taking the limit of. So n cubed on bottom times 1 over n, that's really 1 over n to the 4th. Times that sigma of I cubed. And from there, now we get to replace our I cubed with its formula. So we haven't actually gotten to use that one yet. So let's go back and show those formulas to you guys again. So this will be the very last one here. So it's n squared times n plus 1 quantity squared all over 4. So that's what that sigma is going to get replaced with. Okay, so and again, it's not the whole thing, it is just this part. So the 1 over n to the 4th in front is actually going to stay there. So what we end up with is our area is equal to limit. Yes, you do have to write the limit notation in front of everything to be proper. So then we have 1 over n to the 4th times, it'd be nice if that actually said n to the 4th, times that formula, n squared times n plus 1 quantity squared all over 4. And I just realized I lost the fourth there. All right, now, to do this properly, we should be expanding, multiplying everything out so we have everything. But realistically, if you go back to what we were just talking about, when we took these limits, remember that in the end, this will turn into a rational expression of n stuff over n stuff. So ultimately, it's really just the leading term on top and bottom that actually matter at all. So if you are in a time crunch, or if you really just want to focus on the parts that matter the most, expanding all of this out, while it is nice and proper to do that, ultimately, it doesn't really matter what the whole thing turns into. I really just care about what the biggest degree terms would be. So for example, on top, I have an n squared, and then if I expanded all this stuff out, the biggest degree inside of all of there would be another n squared term. So ultimately, this ends up being an n to the fourth on top, and then on bottom, I have 4n to the fourth. So if I take the limit as n approaches infinity of those two terms, I get my final answer of 1/4. That is the area of that region under the curve of x cubed from 0 to 1. Now, to do it properly, we would want to expand everything. So if we were going to write this out the proper way and not break any notational rules, then when I expand everything out in the numerator, I end up with n to the fourth plus 2n cubed plus 1n squared all over 4n to the fourth. But again, once I see all of that, those extra pieces on top play no part in the limit of this entire expression, because it's still just same degree over same degree, and so it's the ratio of those leading coefficients. So no matter if we write everything out, we're still going to get to that same final answer. All right, so now for our last example here, same idea, just a different function, different interval. So this one's a little bit more difficult simply because of the interval involved. So anytime that your interval doesn't start at 0, it's definitely going to make things just slightly more complicated because of our endpoint formula, and you'll see that here in a second. So for this one, though, we want to find the area of the region bounded by the graph of f of x equals 4 minus x squared, so upside down parabola, shifted up 4. The x-axis, and then the vertical lines, x equals 1 and x equals 2. And again, that's just another way of describing the interval that we are shading for the region. So sometimes they'll just simply write out the interval from A to B, and then other times we'll describe it as the vertical lines. So it's still the same thing. So this is my A, and this is my B value. So first step, as always, I need to figure out a formula for my delta x. That's what allows me to find my endpoints, which allows me to find my heights. So delta x, b minus a would be 1, and then divided by n, again, unknown number of subintervals. So again, we get to choose now which endpoints we want to use. And so even if we start at some value that's not 0, your right endpoints are still always going to be the simplest option. And again, going back up here, again, that allows us to use the easy version of this formula. Again, instead of I minus 1 like we have for the left endpoints, it's just I. So what makes this more difficult now, though, is that a value is 1. So last time we just ended up with one term that I had to substitute in for x because my a value is 0. So anytime that a is not 0, it's just going to make it slightly more difficult when I substitute this formula in. So delta x times I, in this case, would be 1 over n times I, or I over n. So this is my formula that I could use to calculate all the different x values that I could possibly create, which then means I need to substitute that into the function to get the formula for my heights. Again, that's what we're doing here. So instead of 4 minus x squared, it will be 4 minus my c sub I formula squared. Again, this is the formula to help us calculate the x values. So inside of here, I'll have 1 plus I over n. So now I need to expand this and clean this up. So I'm going to have 4 minus the result from this binomial expansion. So square double square would give me 1 plus 1 times I over n times 2, so 2I over n, and then plus our second term squared, so that would be I squared over n squared. I'll distribute the negative to everything, and then these two constant terms can combine. So I really end up with the formula 3 minus 2I over n minus I squared over n squared. So that's our formula for our y values for the function. Again, if I pick a value of I, so which subinterval I'm looking with, that would determine the, or this formula would determine the y value that that particular interval or rectangle would create. Okay, so there's my heights. Over here, again, delta x is my width. So we're just going to multiply those two and take the limit of the summation. So remember, area equals now the limit as n goes to infinity of sigma from I equals 1 to n of heights times width. So 3 minus 2I over n minus I squared over n squared times 1 over n. So just like we've seen in the other ones, first step is I'm going to pull that 1 over n out in front. Again, it's not out in front of the limit, just out in front of the sigma. So again, you can think of there being big brackets here. And then inside the sigma, I'm going to separate and pull out all of the extra stuff. So as you guys get good at these, you don't have to write everything out as one individual step because there's so much writing involved. It's definitely more efficient for us to do this kind of one thing at a time. Actually, I'm going to pull the 1 over n outside of the brackets even, so I don't have to have multiple sets of brackets in here. So 1 over n times the result of this sigma. So again, I'm going to separate. So this will be sigma from I equals 1 over n of just my constant 3. Then minus, for the middle guy, again, we strip away everything that's not an I variable, a constant I squared, or I cubed. So 2 over n is that constant multiple, so that gets pulled outside of this second sigma. So inside I'm left with just I, and then the last guy, we can pull out the minus 1 over n squared. So inside that would leave me with just I squared. Okay? Again, once all the sigmas are set up, now we are going to replace the sigma of constants or the i's with their corresponding formulas. So this is the limit as n goes to infinity of 1 over n times sum of a constant is that constant times n minus, and again, all these things out in front are going to come along. They're just constant multiples, so we'll multiply. So we have 2 over n times the formula for I, n times n plus 1 all over 2. Sorry, that didn't look that great. And then for the last one, minus 1 over n squared. And then again, the formula for I squared, we have n times n plus 1 times 2n plus 1 all over 6. Sorry, that looked like a minus there. And that's it. So now we can go through and simplify this as much as we can. So let's simplify the stuff inside first, and then we'll take care of the distributive property. So these 2's cancel, the n's cancel. And then inside, let's go ahead and cancel out this factor of n with one factor of n in the denominator. So now we're going to distribute the 1 over n to each of these guys, and then we'll evaluate the limit of what's left here. So we've got the limit as n approaches infinity of, so inside, so I'm just going to use parentheses now. Actually, no, let's stick with brackets. Just because I've still got parentheses inside. 3 over n, or excuse me, 3n times 1 over n, that would actually just reduce down to 3, so just the constant. And then minus, so inside, all that's left in this second term is n plus 1 over n. Okay. All right, and then for the last guy, so a minus, but 1 is not going to change anything, but my numerator is just those binomials, so I'm going to go ahead and multiply those out. So that gives me 2n squared, and then plus 3n, plus 1. And then on bottom, 1 over n times this 1 over n times 6 would give me 6n squared underneath, okay? Now, so this one I chose to expand everything, but now, now that it's all written out, when I go to take my limit here, we're really just essentially taking the limit of each of those 3 pieces. So each one of these is going to contribute something. So the limit of a constant is itself, so we get 3. and then minus the limit of this middle guy. So this is where we can really use the growth rate to expedite the limit process. Technically, that would give us infinity over infinity. So if you wanted to, we could use L'Hopital's, but it's going to give us 1 over 1 when I do that. So we can kind of do that in our head or think about growth rate. We've got same over same. So we know the limit of that ratio would just be 1. And then also minus, and then for the last guy, another n squared over n squared, so another same over same. So it's the ratio of those leading coefficients. So 2/6 or 1/3 is what's being deducted there. So we got 3 minus 1, that's 2. 2 minus 1/3 is really 6/3 minus 1/3, or we get a final area of 5/3. And that is our final answer. That is the area under that curve from 1 to 2.